Development Manager, and next to me is sitting Philips Tomschais, our software engineer and today's webinar speaker. The topic of today's webinar is connected to the modal analysis. During the webinar session, you will see a demonstration of modal analysis using stepped sine and using impact hammer. We tried to make this webinar as engaging as possible. That's why we asked our production department to help us and replicate a bone, which you will see later during the test run. To replicate the bone, we used a 3D printer, and it wasn't an easy process at all. We hope that all our efforts were not in vain, and that you will be able to look at the modal analysis from a different angle and conquer your fears about difficulties you may face with modal analysis. Now just a few words about Ruler Technologies. Ruler Technologies is a team of experts in vibration research. The company is a family-owned business located in Riga, Latvia. We mainly manufacture vibration control and data acquisition systems. All our products are manufactured in Europe and meet the standards. We have representatives in more than 40 countries, among which the USA, China, Germany, Australia, Korea, Turkey, and so on. For all our customers and partners, we offer free updates, lifetime compatibility, installation and training, versatile equipment, tailor-made solutions, free online education, agile support 24/7, and flexible warranty terms. And now, without further ado, I would like to give the floor to our today's speaker, Philips Tomschais. Philips, you're welcome.
Hello everyone. In this webinar we are going to talk about modal analysis using stepped sine sweep and impact hammer. And before we start, let me explain some theoretical basics and tell you a little bit more about our setup. So here you see the plan of our webinar. We will discuss the modal analysis application spheres. I will talk a little bit about impact hammer, discuss modes and main definitions for modal analysis. After that, we will discuss our today's setup and configuration and perform modal analysis using impact hammer and stepped sine sweep. So what is modal analysis? All systems have operation conditions like that cause them to respond to certain excitations. The loads can be either static, like for example a beam on which a mass is placed, or dynamic, like a beam vibrating under some external force. Dynamic loads are the concept we need to pay close attention to. They may cause responses that are unacceptable, and we can call them resonances. And our goal here is to find a way to minimize or eliminate this undesired response. Modal analysis is an important tool that helps us to identify these dynamic loads. It converts the vibration signals and responses we measure on a structure into a set of our modal parameters. The mathematics behind modal analysis is rather complex. However, we will make some practical examples and we will illustrate this concept, and today we will demonstrate the capabilities of our modal analysis software. First of all, let's discuss such tool like an impact hammer. It has a built-in sensor. In our case, we have a force sensor. It can have additional load mass and different hammer tips. It connects to the controller like a regular sensor, and using this tool we can perform impact hammer modal analysis on our testing object. Now let's talk a little bit more about the application spheres of modal analysis. First of all, the main sphere is aerospace. Here we know that a lot of aircraft engineers use modal analysis like regular sine sweep modal analysis and hammer impact modal analysis for research on different separate parts of the construction. It is also used in automotive and mechanical engineering. So let's talk a little bit more about the main definitions for modal analysis. And the first one is called mode. Mode is the shape in which structure vibrates or deforms when it's excited at its natural frequencies. Under typical operation conditions, a structure will vibrate in a complex combination which consists of all available mode shapes, and we will discuss all of them. However, by understanding each mode shape, the engineer can then understand all possible and available types of vibrations. For example, if a simply supported beam is excited at its first natural frequency, it will deform to the mode which is called V mode. Here you see that the beam will vibrate like shown here in the picture. And if we influence our beam with its second natural frequency, it will vibrate with S mode, like shown here. And finally, if we excite our beam with a frequency between its first and the second natural frequency, we will get a W mode. Another parameter which we need to pay close attention to is damping factor parameter. The damping factor is a value which describes how oscillations in a system will decay after a disturbance. If there is a spring mass system, then if we pull the mass and then release it, the spring will oscillate with decaying amplitudes. The damping factor characterizes this speed of the decay. Also, we need to know another important parameter, which is called frequency response function. Frequency response function is used to characterize the dynamics of the system. FRF is a measure of magnitude and phase of the output as a function of frequency in comparison to the input signal. Here you see the main scheme, where X is an input signal, Y is our output signal, and H is the transfer function, which describes our FRF. In our software, we have three main calculation algorithms for FRF, H1, H2, and HV, and the selection of them depends on the noise on the input or output channels, or if you have noisy inputs and also outputs, you should use HV. So the selection depends on your system and the setup. Now let's talk a little bit more about the setup. Here you see a frame and a mounted bone model. It has four IP sensors placed on its side. All of them are connected with our ruler RLC21M controller. Also on the right side we have a shaker with a beam. It's connected with a force sensor, and it will be used during the sine sweep run. After that, we will connect a modal hammer and perform modal analysis with impact hammer. And we have some questions.
Yes, Phillips, could you tell us what force sensors do we use and how many sensors can be connected to the device under test?
In our software, we have all available sensor types like charge sensors, IPE sensors, even TADs. We can also connect strain gauge sensors and set a measuring dimension for them. So in that case, you can set any sensor you want, and we don't limit the maximum sensor number. It depends on the how much channels you have on your system. Today we will use 5 input channels of our controller, so it's not limited.
Thank you.
So I think now we can go to our software here, and I will enable camera. So our first step will be performing stepped sine testing. We go to this mode in SignalUp software, wait a bit for the controller connection. Here we have our controller and we need to create a new project. Let's call it webinar Sine. After that, let's set the geometry. Here we need to add 5 points. Four of them will be connected with the reference sensors and one of them for the shaker sensor. So I change the coordinates. And connect them with lines. And I need to change the line thickness. Here we have our bone model. After that, let's press OK and go to the settings of the sine sweep. Here we have the selection of our calculation algorithm, the sample rate, and we need to enter the profile. We will run from 200 Hz up to 1000 Hz with a step of 1 Hz, and we will set the voltage as 0.2 volts. After that, we can change the step type. It can be linear or logarithmic. Change the frequency direction, and now we need to decrease the positive and negative edges and enter the measuring settings. We will set wait time as 3 periods and the measuring time as 5 periods, and we will decrease the number of averaging. We can set this parameter in seconds, milliseconds, and sine periods. After that, we go to the sensors tab, and we need to enter all our sensors. And I need to say when you have one sensor entered, its parameters will be copied to the next line. So here I have more 3 sensors and enter my charge sensor. I change its type and dimension. Its sensitivity is 1.72 picocoulomb per Newton. And now we switch to channels tab, add our channels. They are connected with the device inputs. Change the axis to Z. And connect them with the points. And we need to set the last channel as the reference one. And now we need to create a new series of measurements. And let's set up the gain on the amplifier and start the test. So you see that we have response signal, FRF, frequency characteristics, and coherence graph. Here we can change the graphs for the type you want. And I think you can hear the Sine running. So we need to wait some time. So we have 3 peaks now, and we can say that these are the resonances of our bone, and I think maybe we will have another one. So our measurement is completed. We can switch to our main tab, and here we can make modal analysis project from our measurements. Let's press this button and call it Sine Sweep Webinar Check. After that, we switch to the modal analysis, and let's open our project. Here it is. Here we see the project description tab, our measured data files, the geometry tab with our points. FRF is already calculated. You can select the channel and create a graph, or for example, phase. After that, we need to calculate the modes, and here we select our measurement, go to settings. Here you see all available methods, and if you are interested in maths behind them, write us an email or a request, and we will make a webinar or a video about this. But now we will select the phase resonance. It's the easiest way. Here you see that our start and end frequency are entered, and we press OK and press calculate. And here we see a table of all the modes. Here you can create graphs of these modes, and we have a Q factor which describes the sharpness of the resonance. So let's go to animation tab and select this resonance. Here we enter the desired force. Let's increase it a bit. So I think so. You see it's moving. Let's select another resonance. So I applied a too big force. Let's decrease it. And you see that if we influence our object at the first point at this frequency with this force, it will change its structure like this. So let's stop it and continue with the next stage. It's called impact hammer testing. We set this mode, wait for the controller connection. And let's create a new project. We also need to enter the geometry here. And I will perform shocks at the first point. And I shift the coordinates a bit. I need to connect all the lines. Let's change the thickness. Here we see our line. It's similar with the previous test. Press OK. And we need to set up the settings. Here we have two modes, roving hammer and roving accelerometer. We will use the second one. In that case, we will perform shocks at one point and measure the response with all our measuring sensors. Here we will set the level as 2 newtons. We will leave FRF calculation algorithm and other averaging parameters by default, but I think I will set the number of averaging as 5. After that, we go to Sensors tab, and here we need to enter the sensor. Add 2 more, and the final will be called hammer. It is charge. Here we select force and set it as 1.72 picocoulomb per newton. After that, we go to channels, select our hammer. It's connected with the shock point. After that, we enter 4 points. Enter the axis. Let's create a new series of measurements. Now I need to connect the hammer with the controller and make some preparations. So I think I moved my PC and the connection was lost. Let me refresh the connection. Here we have our controller back. And let's start our measurements. Here we press start. So we will discard this first noise hits. Let's test the shock. Here we see that we capture the hit. And now let's hit our construction. So we accept it. So now we switch the sensor and press next point. We continue to perform the shocks. After that, we switch our measuring sensor again. And go to the next point. And let's switch to our final point. So our measurements are completed. And now we are ready to perform an analysis in modal analysis mode. Here you see the recordings of all our shocks, and we need to press make modal analysis project. We call it something like this. And switch to modal analysis mode. Let's open the project. And now we see all our data files, the geometry, calculated FRF, and you see that we have X here. And let's calculate the modes. We press settings, and I think we will use the default parameters for this algorithm and try to calculate it. And I think using these calculation settings we have such modes, but let's try another parameters like peak picking. And using these parameters, we have another results. I think they are better because we got our resonance at the first point at 944 Hertz, and it's really close with our results from the sine sweep. But you see that at some points we don't have lower frequencies. Maybe it's because we need to stop the vibrations on the bone or something like this. Or you can place an object, find better points for the shock, and in that case you can perform research of your testing object. And now let's go to Animation tab, select our point, increase the force. Let's set it like this. And you see that when we perform a shock at the shock point, all our points will move like this. And let's, for example, change another point. This one. So you see different modes which were calculated, and that way you can perform modal analysis and get the results using SignalUp software. So here you see a table which we see the results of comparison between impact hammer and modal analysis using shaker. The setup time is really quick for the impact hammer. In some cases you can have a sensor with a magnet and an impact hammer, and every point you need to connect the sensor and perform shocks and get the results. You don't have any complex attachment to your structure, and in that case you can perform single parts research. But using shaker you need to find the best places for model shakers. You need to create complex fixture, but in that case you will get the information about full structure excitation. So the best way here is to combine these ways. Like we had higher frequency range with the hammer, but the range from 200 Hertz up to 1000 Hertz was covered with a shaker. So today we discussed our software tools which are necessary to run modal analysis and collect data for it. I showed you new options for calculation FREF, and we have different algorithms for this parameters calculation. We discussed the modal analysis parameters and definitions for them, and we compared two different options for modal analysis. So I think we covered all the questions about modal analysis for some time.
Not all. So I have a question regarding our another device. So we have RLR19, and can we use RLR19 with impact hammer?
Yes, now RLR19 has an impact hammer mode. So in that case, you can get your portable device, one sensor, one hammer, and perform modal analysis everywhere you want. So it's a rather interesting setup, but it is available.
Great, thank you for your answer. We would like to thank you for your attention and for being with us today, for watching this webinar. If you have any questions regarding the modal analysis or any other options which you may be interested in, please write us an email and we will try to answer you as soon as possible. See you next webinar. Bye.